In this lab, the objective was to observe the motion of an object that is dropped from rest and falls slowly to the ground. In doing so, we are able to observe some key principles about Newton's second law, and specifically what kinds of forces contribute to the net force of a system. In my lab, I decided to observe a falling soccer ball. I then used Tracker to observe the motion, construct a position versus time graph, and then use the data to create a simulated version in VPython. In the end, I observed that my experimental data and my model data did match very well. This means I was successfully able to predict the motion of a falling object. However, in order to go into more details about this lab, you first need to understand a basic principle about Newton's second law and the net force of a falling object. When an object is falling, the velocity is not constant. In fact, it is changing at every time interval of the fall. So what are the pushes and pulls that affect the net force? There are two major ones we will discuss. The first one is weight force. Weight force, also sometimes referred to as gravitational force, is the force that the Earth exerts on the falling object. Because gravity is always pulling downward, weight force is responsible for the pull of the ball as it drops. Weight force uses the object's mass as well as a gravitational constant to calculate how much the Earth is affecting the object. The second force that acts on a falling object is drag force. Drag force, also sometimes referred to as air resistance, is the force that the air exerts on a falling object. As an object drops through the air's resistance pushes upward, which is why drag force is responsible for the push on a ball as it drops.
Now that you have a basic understanding of the physics behind this lab, here is my recorded video of a friend dropping a soccer ball that I have loaded into Tracker. Making sure to use the calibration tool to set the diameter of the soccer ball, and the coordinate axes tool to drop my ball in the negative y direction, I tracked the center of mass of the soccer ball. I used the center of the ball to do this, and as you can see, as the ball is tracked, the graph produced to the right shows a curved line, indicative of an accelerating object. I then moved on to creating a predictive model of this motion in the VPython program. I entered the mass of the ball, the initial position, based on where I set my coordinate axes in the tracked video, and the initial velocity. Because the ball was dropped, the initial velocity is 0. The time that I started the video was 0 seconds, so t is set to 0 in the code as well. The gravitational constant is set to 9.8 meters per second, and the j-hat direction is set to the y direction, as the soccer ball fell along this axis. My drag force constant b is set to 0.12 due to a trial and error process I followed in order to match the final velocity of my experiment with the final velocity of the model. The loop is limited to while t is less than 0.6 seconds, or the total time of my video. Originally, I only included weight force in my calculation of the net force. When the code was run using only the weight force, you can see from the graph that the model over-predicts the position of the falling soccer ball. This is because weight force is not the only force acting on the ball. As we discussed earlier, drag force also contributes to the net force of a falling object. So I adjusted my code to include drag force. As you can see from the code, drag force is equal to the negative of the drag constant multiplied by the magnitude and direction of the velocity. I then adjusted my net force and also updated my ball.vel and ball.pos variables to reflect Newton's second law. After running this code to include both forces, I got a slightly different graph. As you can see in this graph comparing weight force alone to weight force and drag forces, we can see that as the ball continued to drop, drag force began to increase with increasing time and had more of an influence on the velocity of the ball. This final graph compares my experimental position, the blue line, to the model position when Fnet only includes weight force, the red line, to the model position when Fnet includes both weight force and drag forces, the yellow line. As you can see, while the red line over-predicts the position of the ball because it takes into account only weight force, the yellow and blue lines are both a very good match. This means that my experiment was very good at predicting the motion of a falling object when both weight and drag forces are calculated into the net force of a falling object. Here's a visual representation of my experiment using my code from VPython. You can see that as time progresses, the magnitude of the drag force pointing upward increases. Do either or any of my models predict a terminal velocity? To answer that, let's take a deeper look into what terminal velocity is. Terminal velocity occurs when the drag force is equal to the weight force on an object. In order for the combined weight and drag force model to be able to predict terminal velocity, this experiment would have to be much longer. Therefore, weight force is a pretty good indicator of terminal velocity. If the soccer ball were initially thrown downward instead of dropped, you might think that the terminal velocity would change. This, however, is not the case. The terminal velocity is the same regardless of whether you drop or throw an object. What does change, however, is how fast it reaches terminal velocity. As you can see in the graph produced from the VPython data, calculating the position versus time data for a thrown object and a dropped object, you can see that the thrown ball, which is the blue line, reaches the terminal velocity much faster than the dropped object, which is the red line. However, the dropped object would also be able to reach terminal velocity given enough time. As you can see, the thrown object's velocity is pretty much a straight line, at the end of the graph, indicating a constant terminal velocity. The dropped object's velocity is still curved, indicating that further acceleration to terminal velocity is possible given more time.